All right, let's talk a little bit more in the second part of the video here about complex power again, because it's really important. So as I said before, if I have a general impedance, right? So just any impedance could have some resistance, inductance, capacitance. That impedance has a magnitude and an angle. Okay. So in the time domain, we have a voltage that's written out like this. So it's got a peak voltage, V peak, cosine omega t plus phi sub v. Right, so because we know that V RMS equals V peak divided by the square root of 2, we know that we can write our phasor. In this case, we've said that we've started writing our phasors as having an magnitude that is given by the RMS value of the waveform. And similarly, we have a current that is I peak times cosine omega t plus phi I, so we write its phasor in terms of IRMS as well. All right, now at the end, in our previous video, we defined what we called the complex power, right? We had these terms P, our active or real power, and Q, our reactive power, that could be written out like so, right? We said that they form this vector we call complex power, which has a magnitude S, and it has the same angle as the angle of the impedance, right? And by Ohm's law, V equals IZ, we have phi V equals phi I plus phi Z. So phi Z is equal to phi V minus phi I. What we see here is that the complex power forms this vector where the vector itself is called S. The imaginary part of it is Q, the reactive power, and the real part of it is P, the active power. This is why we call it the real power, because it's the real part of the vector. Okay, so let's look at some typical loads, all right? And so the only kinds of loads we typically have when we're talking about power, usually traditional power at least, are loads that are resistive, capacitive, or inductive. So a resistor obviously has a magnitude of its impedance that's R and an angle that's 0. If I have an inductor, it's j omega L, which means it has a magnitude omega L with an angle of 90 degrees. And if I have Z sub C, that's 1 over j omega C. So the j on the bottom can be turned into a negative j up top. So that means that this guy has a magnitude 1 over omega C and an angle of negative 90 degrees, okay? So in general, our loads aren't just a pure resistor, inductor, or capacitor. In general, there's some combination of the both. Now, one thing I will say is in practice, you almost never see a pure L or a pure C because they don't really do anything. They just basically take in energy and then give it back, take in energy and give it back. Most things that I have, like motors, heaters, lamps, computers, really are primarily resistive, but we always have some element of L's and C's hanging around, particularly if we have motors, which are a lot of the large loads that are out there in the world. Okay, so let's look at if I have an inductive load. All right, so if I have an inductive load, what I mean is that my Z equals R plus J omega L. Now, in that particular case, I have a real or a positive real part and a positive imaginary part. So inductive loads are going to be here in the first quadrant of the complex plane. All right, that's where their impedance lies. If they're in the first quadrant, that means my angle is always between 0 degrees and 90 degrees. Okay? If I have a capacitive type load, I have a positive real part and a negative imaginary part. So that means I'm always going to be in the fourth quadrant. I'm always going to have capacitive loads down here. So if I'm always in that quadrant, I can say that I'm between 270 degrees and 360 degrees, or a more typical way is to say that I'm between negative 90, which is down this way, right, and 0 degrees. Okay? Now, one thing it's important to note is loads should never have a negative real part. I say loads should never have a negative real part. That would mean that they have a negative resistance. All right, that can happen, although it's it really requires some funky electronics for that to happen. But in this class, we won't talk about that. That's something you'll deal with later on in your time if you're dealing with things like in controls and those sorts of classes. All right. In general, we're going to deal with loads that always have a positive real part. But my imaginary part can be either positive, meaning that I'm inductive, or negative, meaning that I'm capacitive. Okay. Let's focus in first on these sort of inductive type loads. Okay. So as we said, we have a positive real part, a positive imaginary part. So that means I'm in the first quadrant with my impedance. Okay. And I want to figure out a little bit about the relationships here with the current. So we've said our voltage phasor has a magnitude VRMS and an angle phi sub V. Okay? So if I look at my phi sub I here, all right, if I use Ohm's law to figure out what I is going to be, I equals V over Z. So that tells me my magnitude is IRMS. All right, that magnitude would be, if I wanted to figure it out, would be VRMS divided by the magnitude of the impedance, whatever it is, right? The angle here is phi sub V minus phi sub Z, right? Is the angle of the current. So phi sub V minus phi sub Z. Because of the fact that my angle is always going to be positive, right? I'm always subtracting a positive angle from the voltage to get to the current, okay? Always subtracting a positive angle. So that means that my current will I always have to go backwards from the voltage to get to the current. All right. As a result of that, we say that the current I lags the voltage V anytime I have an inductive type of load, right? In other words, I have to go backwards to get from V to I. So we say that I lags V. All right, so for our power terms here, if I look at this cosine phi V minus phi I, so the angle here is phi sub Z. Again, I can just use Ohm's law to figure that out, right? That's always going to be positive, right? Because I'm in the first quadrant with my phi sub Z. All right, so my P is always going to be real, right? My Q equals, in this case, VRMS IRMS sine phi V minus phi I. Well, phi V minus phi I is phi Z, as we said. So because we're talking about an angle that's between 0 and 90 degrees, my Q is also going to be positive. So that means my complex power, S, is always in the first quadrant. Okay? So I have an angle, so my impedance and my complex power are always going to be in the first quadrant when I have these inductive type loads. And we say that the inductive loads have we call a lagging power factor because the current is behind the voltage. The current lags the voltage. So we'll talk more about this terminology of lagging power factor here in a minute. So if I have a capacitive load, right? For a capacitive load, we said we have a positive real part, right? And we have a negative imaginary part. So that is somewhere down here in the fourth quadrant. All right, so our impedance is down here. Right, so that means our angle is between negative 90 and 0 for the impedance. So my voltage, if it has a phasor with a magnitude VRMS and an angle V, and I go through and I do my Ohm's law again, I say that the magnitude of this is IRMS. And as we said before, IRMS will always be, in this case, VRMS divided by the magnitude of Z, whatever that may very well be. And the angle, just again, is angle of the top minus angle of the bottom. Okay? Phi V minus phi Z. Important thing is because phi sub Z is always negative, we're going to be adding a positive number to phi V to get to phi I. So in other words, I leads voltage. In other words, I'm adding a positive angle to V to get to I. So in this case, I would be somewhere over here, right? So I'm moving forward. I'm moving in the counterclockwise direction. That's the positive direction, okay? So in this case, phi sub v minus phi sub I, which we call the impedance angle, all right? So when I'm looking at angles down here in the fourth quadrant, that's the p-value is going to be positive again, meaning that active power is absorbed. For my q value, again, sine of phi sub z. So if I'm taking the sine of an angle here in the fourth quadrant, that's going to be negative, all right? So what that means in this case is my q is negative, which means that for a capacitor, it is sourcing reactive power. So the S I have is down in the fourth quadrant. It has a negative q value, which means that I am supplying reactive power, right? My capacitor supplies reactive power. And so it's a negative q. If I compare that to the inductor, I had a positive reactive power, meaning that it's sucking in reactive power, as opposed to this guy is supplying it, okay? So capacitive loads are said to have a leading power factor since current leads the voltage. Now this terminology about delivering reactive power or absorbing reactive power is really important if we talk about how the power grid works. And we'll look at some examples of that later. All right, so let's talk again about power factor. I've mentioned that before, but power factor is defined as this sort of cosine relationship, the cosine of the angle between the voltage and the current, right? Which we say is simply just the cosine of the impedance angle, right? Again, using our Ohm's law relationship, where we know that phi sub v is always phi sub I plus phi sub z, right? V equals IC. So a couple of things. We know that for a resistive load, the current and voltage are in phase. So in other words, phi v and phi I are always the same. So the cosine of phi v minus phi I is the cosine of 0. The cosine, so the power factor here is the cosine of 0 degrees, or 1. So we say that for a resistive load, the power factor is unity. Now for a pure inductor, it's a little bit different. So for a pure inductor, I would have that phi sub z is equal to 90 degrees, right? So again, using my Ohm's law relationship here, phi v minus phi I is 90 degrees, okay? So my power factor in this case is cosine of 90 degrees, or 0, okay? So it's 0 power factor in that case. For a pure capacitor, what we say is it's cosine of, so for a pure capacitor, phi sub z is negative 90 degrees, right? 1 over j omega c. This too is cosine negative 90 degrees. Cosine of negative 90 degrees is also 0. So if I look at a pure inductive load, right, which is going to have, so I say pure inductor, I mean I just have an inductor. For an inductive load, I say I have R plus j omega L, so a positive real part, positive imaginary part. My angle is somewhere between 0 and 90. That means my power factor is somewhere between 1 and 0. For a capacitive load, where my angle is between negative 90 and 0, if I run through the math that I just did above, my power factor is still between 0 and 1. To differentiate between, so I could have an inductive load with a power factor of 0.5, and I could have a capacitive load with a power factor of 0.5. Sometimes we say that inductive loads have a power factor that is lagging, because I lags V. And in the case of a capacitive load, we sometimes say the power factor is leading, okay? So to sort of begin to summarize all of this, okay? So if I have some element here in an AC system that is being provided with, S equals P plus JQ going in, that's the definition. So I have a voltage here at the terminal, plus to minus, and a current defined to be going in. Using my passive sign convention, that means my S equals P plus JQ, okay? So in this case, if I have an inductive load, the impedance angle is going to be somewhere between 0 and 90 degrees. P is going to be positive because I have a load and power is being absorbed by a load. For an inductive type of load, S P plus JQ is an angle that has the same angle as the impedance. Okay. All right. And so Q will be positive for this guy. We said that I lags the voltage and it is absorbing reactive power. So if I have a capacitive load, meaning my angle is somewhere in the fourth quadrant, power is still absorbed because I have a load and it should be absorbed, so power should be flowing in and P is positive. But in this case, Q will be negative, all right, which means that this guy is sourcing or delivering reactive power to the network. And I has been shown to be leading the voltage, meaning that the angle of I has a more positive value than the angle of V. Okay? So some more relationships. We can derive all kinds of stuff all day long, but we knew that in DC circuits we had three key relationships we got from Ohm's law, right? P equals VI, P equals V squared over R, and P equals I squared over R. All of these use the fact that P equals VI and voltage equals IR. You can manipulate this all day long to get these three relationships. For AC circuits, you can use Ohm's law to go from my standard form here to two other forms, which look really similar, right? So in DC circuits, I had I squared R. So in this case, I can use for active power IRMS squared times the real part of the impedance. Or I can say that the active power is the voltage squared, the RMS value of the voltage squared, divided by the real part of the impedance. And remember, if I have an impedance, let's say, inductive, R plus J omega L, the real part of Z is some resistance, okay? So these formulas here look awfully similar to the ones we had up there, okay? Now, similarly, for reactive power, right, what I have is IRMS squared times the imaginary part of Z, all right? And I can also write it in terms of this V squared over impedance form, okay? So I don't need to belabor that. I don't want to spend a whole lot of time on this slide, but it's probably the one that you will want to see, right? If I look at this, it tells me, summarizes for inductive load and capacitive load, what are my P and Q, what's their direction, defines for me active power and reactive power and the different forms that I can take for these things. And then remembering that apparent power, real or active power, reactive power, what all their units are and what the different relationships are between them. There's a lot of different relationships, but they're all relatively straightforward. So hopefully you won't get too overwhelmed by them. All right, because there are quite a few. Now what we need to do is begin to focus on solving problems.